Okay, let's continue the lecture. So we talk about photolithography. After the exposure, and we can do development to dissolve away the photoresist we don't want, and to retain the material we want, and for protection for the etching process. The exposure process, actually, typically we will use three different kinds of optical system for exposure. Okay, so the first one we call it like contact printing. For the contact printing, from the light source, the light source will be bring up into a more uniformly distributed light source by through a lens, and also the mask will be in contact with our wafer, the substrate directly. So the exposure will be directly transfer the pattern from the mask onto the substrate of the photoresist. The second one called optometry exposure. So in this case, we have some kind of space between the photo mask and the photoresist. The difference between these two is, for the first one, we can transfer the image of the mask much better in resolution and also precision from the mask onto the bottom substrate. But the question is, if we have a very tight contact in the photoresist and also the mask, some of the mask material or the resist can be damaged during the contact process, because we need to consider we not only to fabricate once, we need to fabricate thousands of wafers per day. Sometimes we need to have a very frequent contact for your photoresist to the mask. So that's why some people are using this kind of approximation of optometry printing. So in this case, we have some space between the mask and the photoresist. But in this case, you will get some diffraction problem. So the image cannot be fully transferred onto the substrate. There will be some diffraction image problem. So the image will be not exactly the same. Okay. And in the IC industry, people try to use in the projection printing. The projection printing, they using another lens between the mask and also your resist. So they can further shrink down the image like 10 times and then print out onto your substrate. So the good things for this kind of printing is we can using lousy mask. For example, the resolution only 10 micron. After 10 times reduction, you got a 1 micron resolution button. Yeah, it sounds quite good. But the bad side is area will become smaller, exposure area will become smaller, 10 times smaller. So you need to repeat this process many times, okay? But the feature size can be smaller. That's the benefit. The projection printing is more expensive because the whole image system will consider a lot of much more complex lenses inside, and also the optical design is not that popular in school. So in school, usually we using this in our school. Okay, then we after the first step, the photolithography, understand the first photolithography process. Then we go on to the next process, thermal oxidation. The thermal oxidation means we need to grow silicon dioxide onto the silicon surface. So usually this process will perform at a high temperature, because the silicon can be oxidized during inside in the atmosphere at a low temperature. However, until some kind of thickness, it cannot grow anymore. Okay, so if you want to grow thicker silicon dioxide and in high quality, we need to bring the silicon to the high temperature environment. And the silicon dioxide melting point is pretty high. It's 1,700 degrees C. And the interesting thing is when you want to grow 1 micron silicon dioxide from silicon substrate, you will take out the 0.44 micron silicon. That means because you introduce external oxide atom into the silicon, so the silicon dioxide expand than the original silicon itself, 0.56 micron. So remember, so the whole structure will be expanded. Okay, so the structure will become thicker than you think. Okay. Talking about thermal oxidation is will go through the diffusion process. You need to diffuse the oxide onto the surface to react with the silicon, then form silicon dioxide at high temperature. So the diffusion process, the diffusivity is important. So we need to consider diffusivity of different gases. So the diffusivity defined by this equation. So exponential to the energy, the activation energy over temperature. Okay, and this is a diffusion constant here. Okay, so when you draw this diffusivity according to different temperature, you can gather this kind of picture here, the figure here. So first we can see as the temperature increases, the temperature, the table, this figure has been drawn in the temperature on the bottom, inversely proportional to the temperature. So when you go this direction, the temperature is increasing. Okay, you consider this way, be easier for you to understand. So for first, you see for different gases, for hydrogen, sodium, oxygen, water. So you can see at the same temperature, for example, like 1,000 degrees is here. Okay, you can see they have much different diffusivity. So sodium has the highest one, and the hydrogen second. Oxygen and water has a lower diffusivity. And when you increase the temperature, you also can see the increment of the diffusivity for of different kind of gases or ions or atoms. Okay, so these are the first two things you can understand. So that means for different material or for different gases, the activation energy is different. So for hydrogen and the sodium, they have a lower activation energy. So at lower temperature, they can have very high diffusivity. Okay. And as the temperature increases, they also have a higher diffusivity as well. Okay, so so here we will concentrate on the oxygen and water because in the next step, I will introduce for the oxidation, silicon oxidation process. Basically, there are two different types. We call the dry oxide or wet oxide. For dry oxide, actually the silicon grows silicon dioxide in only oxygen environment, dry oxygen environment, no water involved. Okay, but in the wet oxidation process, actually we introduce water into the system. Okay, that's basically the differences. So remember here, so oxygen has a higher diffusivity than water. However, when you do the experiment, you will find out the wet oxide grows faster than dry oxide. It sounds very weird, right? Okay, actually the reason is like that because you grow dry oxide on the surface, silicon dioxide on the surface, the silicon dioxide will become very high density structure, high density material, because it's only pure oxygen reacted with silicon. So you form very pure silicon dioxide material on the surface. The structure is so dense. So once you have this kind of thing on the surface, you will prevent the diffusion of the oxide, further diffusion into the surface. So the growth rate becomes lower and lower. It's not easy. But for wet oxide, okay, you introduce water, okay, as a reactant. So when they form silicon dioxide, it's not pure silicon dioxide. Some hydroxyl group, OH group, will form inside the silicon dioxide as well. So they provide a channel for water to easier to penetrate the fin, the wet oxide fin, to contact with the bottom silicon for further oxidation process. So that's why you can see the water has a lower diffusivity, but the wet oxide grows faster okay, than dry oxide. That's a reason. Okay, so no matter what kind of oxidation process you are using, you are still going through the diffusion process. So now we will consider the diffusion process. So for kinetic of the oxidation growth, you can consider we have a silicon substrate, pure silicon substrate on the right-hand side. Okay, so I draw only a very thin layer. Actually, it's a thick area, very thick area. Okay, on the right-hand side, and in the middle we have a silicon dioxide layer. So this is silicon layer, this is silicon dioxide layer, and outside the silicon dioxide surface, we have a gas, oxygen gas, either oxygen or water vapor contact with the surface. So in this case, a high concentration of oxygen on the surface. So here give you a concentration of, like, for example, like a N0, okay, on the surface. And because it's a diffusion process, so a concentration gradient can be generated according along this silicon dioxide depth. So on the surface, we have a N0 concentration. So on the surface of silicon, we got N1. So N1, the concentration is lower than N0. Okay, but we don't know what's the number of N1. We just understand this gradient. So because of this gradient of the concentration, so this gives a driving force for oxygen to penetrate through this silicon dioxide, diffuse into the inner area. So here, of the gradient, this gradient can provide a driven force to give a flux of oxygen. So the flux we call J, the oxygen flux. So according to the Fick's law, the flux of the oxygen in this system will be proportional to the concentration gradient along the x-axis, okay, and times the diffusivity. Actually, this is the first equation you can get. So if we consider the concentration distribution is a linear, it's not a nonlinear thing. So we want to simplify the model. Okay, so we consider it's a linear type. So if it's a linear type, it becomes easy. The concentration gradient you can be represented by using these two, the top surface and the bottom surface concentration divided by the distance here. Okay, so the round n rounds will become N0 minus N1 over X. Okay, so this is the first equation you can get. Okay, because N1 we don't know the number here, so we try to replace N1 with different things. So now we consider the reaction rate on the surface. The N1 will depend on the reaction rate because if we more oxygen into the silicon, become silicon dioxide, the concentration of N1 will be reduced. Okay, so N1 will depend on the reaction rate on the surface. So here I can give you the second equation. The J, the flux on the surface will be proportional to the concentration on the silicon surface, N1. You have a more N1, you have a more oxygen can be react with the silicon surface to become silicon dioxide. So from 2-1 and 2-2, these two equations, both of them we have N1 inside, right? But we don't know why is the N1 here. So we can incorporate these two together to take out N1 to get the final the flux without N1 represented inside the equation. So the flux, the final flux, will be proportional to the surface concentration of the oxygen, and also the ratio between the diffusivity of the oxygen and the surface reaction rate, D over K. Okay, it's a diffusion and the surface reaction rate. So you have a high reaction rate, diffusion rate, so the limitation of the whole process will be dominated by your surface reaction, dominated by K. Okay, so vice versa, if your diffusion rate is low and the surface reaction is high, so the total process will be dominated by your diffusion, the lower speed process. Okay? So the physical meaning of this equation gives us this, like what I mentioned. Okay, so here I got the first equation, the flux proportional to the ratio to the distance. However, finally, want to understand the profile, okay, of the concentration along the surface. So, and also the growth rate, the x. So we will use another rule. So the thickness grow on the surface, the SDT depends for different times. So the thickness will grow according to the time. Okay, so this dt will be equal to the J, the flux. So when the flux of oxygen go onto the surface, So what's the thickness will become? Okay, will it become? So the thickness will become the total flux divided by the volume density of this kind of material. So if J over N become the unit become the linear unit, that means the thickness of the oxide grow on the surface. So when you equate these two together, so the J is from the above equation put here. So you finally will get the pure equation between your thickness and your time. Okay, that's the equation here. So this equation can be solved because in addition to x is the only variable, others are constants. Okay, or some kind of a surface concentration conditions. So those things can be predicted. So now we can see this equation and get a final result like this. It looks very complex. Okay, equation finally here. So when we look at the equation, we want to look into two extreme conditions to understand the physical meaning. The first condition is when time is very small. That means we just started the process. So when we just start the process, when time is small, and we can consider this equation here, we can use Taylor expansion to expand the whole equation. So we got the first order term, second order term, third order term. So we take out the higher order term and leave only the first order term. So we can find out that the final equation, x will be exactly proportional to the time. That means the growth in the beginning, the growth is a linear relationship. Okay, as time go on, so you grow more oxygen, silicon dioxide layer on the surface. The relationship is a linear relationship. Okay, so in this case, because diffusion is not a problem, you have only very thin layer of oxide layer on the surface, so you can diffuse a lot of oxygen onto the surface without any problem. So the process will be limited by reaction on the surface. Okay, so in the reaction limit case, we have the relationship between the thickness of the film, linearly proportional to the time. Okay, so that's when the time just start, very short time. However, for a long time, when time become very long, okay, so you got a term much larger than 1. So you can take out the 1, okay, and leave only the rest 1. So you got the final result become the bt squared. B is a constant when you combine those things together. So in this case, the thickness the growth rate will be proportional to the square root of your time. That means the growth becomes slower and slower. Beginning become very fast. The growing process is very fast because it's a linear relationship. But when time go on to a long time, it becomes slower and slower. Okay, so if you connect these two different kind of profile together, so you got a total profile, originally linear, then finally square root. So the between things can be different kind of relationship, but you can connect these two profile together by using some smooth line. Okay, so that's a diffusion process. So that's why every time when you see the diffusion originally grow very fast, then gradually become slow and stopped, almost stopped. Okay, because your silicon dioxide becomes thicker and thicker. Okay, so diffusion become very a problem every time goes on. So when we draw this relationship, the equation here, by using logarithm scale, so you can see we have two types of oxidation process. We call the dry oxide and wet oxide process. So you can see for those curves for the dry oxide, the growth rate is much lower than the wet oxide by at least 1 order of magnitude. For example, if you have grow 10 hours, okay, the same time for 1,000 dry oxide, so you can see the thickness is only like 0.2 micron after 2 hours. 10 growth of dry oxide at 1000 degrees C. So at the same temperature for the weak oxide 1000 degrees C, you can see the thickness will become almost a 2 micron, 1.0 to 2 micron between. Okay, it's become much thicker. Okay, so you can see the dry oxide, the growth rate is much slower. Okay, much smaller than the oxide process. But also it's very straightforward. When we increase the temperature for either dry oxide or wet oxide, we can also see the increment of the growth rate as well. Okay, so diffusion process is also temperature sensitive process. Yeah, so if you increase the temperature, diffusion rate will be increased as well, and also reaction rate will be increased as well. Okay, so this is for the oxidation process. So this is only for the oxidation process when they occur on the pure silicon surface. However, if you have some impurity inside your silicon, the growth is not that straightforward anymore. For example, if you inside silicon you have a boron, you double the boron already inside the silicon, and afterward you form silicon dioxide on the surface, because the boron inside silicon dioxide like the the silicon dioxide like a boron. Okay, actually, they absorb the boron inside silicon dioxide. We take out the boron. So originally you have a flat distribution of your the boron concentration inside the silicon, but after grow oxide on the surface, the oxide will take some boron into this region. So in that case, you got a higher boron concentration in your silicon dioxide area than on the silicon surface. So your profile will change. They will change your functionality of your gate or your source or drain. Okay, consider that. And the first case, the first and the second case, the difference is the first case, you doing the boron, doing the silicon oxide, the annealing process inside ambient. The second one is inside the hydrogen environment. So in the hydrogen environment, the boron will be cast out from the silicon dioxide. So in this case, the total concentration will be reduced because it casts out from here to outside in the phase process. But however, you still have a higher concentration of boron inside silicon dioxide than inside the silicon surface. Okay. So the bottom two represent if the original impurity are not the boron, the one like to being taken out inside the silicon dioxide. So these two represent the impurity the silicon dioxide does not like. They want to reject this kind of impurity. For example, like phosphorus or arsenic. For phosphorus or arsenic, actually silicon dioxide does not like them. So when you grow silicon dioxide on the surface, so the silicon dioxide will keep reject the phosphorus back into the silicon or to outside. Okay, so in this case, the phosphorus will be piled up on the surface of silicon. So you get even more concentration on the silicon surface here in this case because it has been rejected from your silicon dioxide, the phosphorus. And for arsenic, it's a little bit different because he rejected from the surface faster. So will be rejected not only into the silicon dioxide but also ejected out. Okay, so in this case you got a very low concentration of silicon on the surface, but almost no any arsenic on the silicon dioxide. Very strange, right? So the profile will be totally different. So if you already deposit phosphorus inside the silicon, you got a pile up here. But if you have arsenic, both of them are N-type material, N-type impurity, but you got a much lower concentration here. In this case, the behavior is totally different. Yeah. So when you have an impurity inside silicon, when you do the oxidation process, you need to consider this kind of effect. Okay. Otherwise, the control of your source and the gate will be source and the drain will be not accurate. okay, the concentration will be not accurate.